So today is a very important concept I want to introduce to you. It is such a robust and powerful concept. It has to do with energy. It is so powerful because after the laws of quantum mechanics were discovered in the subatomic world, we basically gave up on many notions. You must have heard that particles no more have definite position and momentum. Therefore, forces are not well defined. If particles no more have a definite velocity, it means acceleration is not also definite. So forces cannot be well defined. Now, a long time ago, scientists were studying nuclear reactions and they discovered that the energy they started the nuclear reaction with didn't match the energy after the reaction. So Niels Bohr, the father of the atom, suggested that the energies didn't match because maybe the law of conservation of energy was questionable. Maybe it didn't work the way they thought it did. But then another scientist called Pauli, Wolfgang Pauli, strongly suggested that he could even put his money on the line because he strongly believed the law of conservation of energy always worked and it works. That is why it is such a robust concept for today. Welcome to my advanced physics class where we discuss modern physics and classical physics. Kindly subscribe, click on the notification bell, comment, share, like my videos. We are going to make this lesson so natural, meaning I'll start from where we got all these quantities from, how physicists stumble upon these ideas we are yet to discuss. And first off, we ask the question, if a force acts on an object, what does it do to the object? And one of the answers is a force that acts on an object changes the object's velocity. That is the speed in a specific direction. So if I push on this very hard, you will see it moving in that direction. That is one effect of a force. But I want to ask again, how much does it change the velocity? So this force is a constant acting on any object. Could be this object here, changing its velocity in that direction. Now, if this is a constant force, then it will give it a constant acceleration. And from Newton's second law of motion, F is equal to mv, the constant A will be equal to F out of m. That is the first point. The constant force acting on an object, say on a surface which is frictionless, it will give it a constant acceleration. And that acceleration, which is a change in velocity, will be equal to that constant force divided by the inertia. Then let's plot this constant acceleration into Newton's third equation of motion, which reads v2 squared, we are changing notation, is equal to v1 squared plus 2 times a delta x in one dimension. This is Newton's third equation of motion. And in my previous videos, we have discussed this thoroughly. Now, in place of the a, let's put the f out of m. And let's see where the mathematics take us to. So we have v2 squared is equal to v1 squared plus 2 times a, which is now f out of m delta x. Now we multiply through by m and then divide through by 2. The resulting equation will be half mv2 squared equal to half mv1 squared plus f delta x. It is below the scope of this class to explain some of these operations because they are basic. They are very basic. Now, making f delta x the subject, We have F delta X to be half mv2 squared minus half mv1 squared. So the math is telling us that the product of that constant force that acted on the object, the displacement of the object, is equal to a change in a certain quantity. In fact, we wanted to find out how much the velocity changes, and it changes as a square of the velocity. And some quantities are appearing here. And it turns out that in physics, anytime we stumble upon a new quantity, we give it a name. So the quantity we've stumbled upon here is half a mass times a v squared. Of course, you must have heard it is called kinetic energy. So a force pushing or pulling on an object gives it a change in the kinetic energy, half mv squared. Rewriting this equation, we have F delta X. And we give this to a name, calling it work done. So physicists like to call it work done, meaning the force has done work on the object. It's either pushed it or pulled it, giving it acceleration. And that work done reflects or manifests itself as a change in the kinetic energy. We give the symbol K to kinetic energy and delta K for the change. Kinetic energy, which is equal to K2 minus K1. The whole of this is called the work energy theorem. The work energy theorem states that when a net force acts on an object, it gives it a displacement. And the product of that force and the displacement gives it a change in kinetic energy. So work done manifests as a change in kinetic energy. That is a work energy theorem. In fact, if we graph this, if we graph the force, the constant force against the displacement axis. So let's call this the force axis and then the displacement axis. Now the force is a constant throughout. There's a constant throughout. And so if we call this interval delta x, that is from one point to another point on the displacement axis, and then this is a constant force. The constant force has this value. Now F delta x is tracking how much area you cover under this graph. In fact, work done is an area function. So F delta x, as you can see, is the area of this rectangle, and manifesting as a change in kinetic energy of the object. So if you know the displacement a force moves an object through, and if you know the constant force, you can predict how much the velocity will change. Same way, if you know how much velocity changes from one point to another, then knowing the displacement, you can also see how much constant force was applied. Okay. But then this equation works even when the object moves miles away, given that the force is a constant. But what if the force is a variable force? That's our next thing to study. And nature presents us with many forces which are position dependent. Forces which depend on position. In one dimension, it depends on, say, x or say y. Basically, almost all the forces we know in nature are position dependent. The spring force is position dependent. The electromagnetic force is position dependent. The gravitational force is position dependent. The weak and the strong forces, that is the nuclear forces, are also position dependent. And The only force which is somehow tricky is friction. And even with that one, given a specific direction, it is position dependent. Other than that, it is a velocity dependent force. So let's study a variable force connected to the work energy theorem. So now the force under study is no more a constant, but it varies with position. And let's say it could be the spring force. The spring force is position dependent, is equal to negative kx from Hooke's law. So when such a force acts on an object, how much does the velocity change? Does the velocity change? In fact, this time round, you cannot simply multiply the force by delta x as the area of a rectangle, because the force varies at any point. And if we graph this force function, which is a position function with the displacement axis, now you're going to get this negative kx. So at each point, the force is different. At this point in x, the force is like so. At this point, it is much a bigger force. At this point, much bigger force. So you see, the area you are going to calculate would rather be an area of a triangle and not a rectangle. So what is a general way to come out with an explicit formula for the work energy theorem for a variable force? This is especially for kind of a spring force, but it could be any other force at all. Okay, for that one, let's create any force function with these dimples and ups and downs. Let's call this our force, which is position dependent, and let's call this our displacement axis. Okay. And the work energy theorem says that the force multiplied by displacement is a change in kinetic energy. But here the force is varying from one point to another. Okay. But then we can choose to be mathematically smart by picking an interval in x. Let's call that delta x. So that is x1 to x2, so close together. And the word I prefer to use is infinitesimally close, delta x. And then we realize that with that infinitesimal displacement, delta x, at that point, the force can be approximated to be a constant. That is hitting this part of the curve, F, at that point, x. You see, now if we go miles away, if we pick an interval from this point to that point, you see, the force wouldn't be a constant, because the dimples and the ups and downs would appear. But if the displacement is so infinitesimally close, then we can approximate the force to be a constant, F at that point, x. Then the force multiplied by the displacement will be the area of that small rectangle. So the F at that point, x, multiplied by the delta x, will be the area of this rectangle. And in fact, let's call this x1, then call this x2. So that will be a little change in the kinetic energy. Let me call it delta k. So k at x2 minus k at x1. You see. So then if we even make this much smaller than delta x, then we are entering a new branch of mathematics called integral calculus. So we can make delta x so tiny, let's call it dx. So then f of x times dx is equal to a little change in kinetic energy, dk. That's what we have now. You see. So now we are going to widen our interval. We have now picked a very tiny interval dx. And if we call this position x1, then we can call this x1 plus dx. So this point is x1, this point is x1 plus dx. See, let's say we want to calculate how much work the force does from x1 to a much wider displacement, say x2 at this point. That means we need an area from x1 to x2, that is at this point. How do we calculate this area, given that it is an irregular shape? It is a much difficult proposition, but calculus does it so easily. Now, so easily because as we found a little interval dx, we can find more dx's and calculate those tiny areas and add everything up. And if we do that, we call it an integration. This elongated s stands for summation of all those tiny areas. So we have f of x dx is equal to the integral of all the kinetic energies. See, from x1 to x1 plus dx, you would have the kinetic energy at this point minus that. You pick another interval, you have that kinetic energy minus that one. So eventually, all those intermediaries will cancel out. And the only kinetic energy that will turn out to be the difference will be this k2, or k at this point x2 minus k at this point x1. So this will be equal to the whole delta k that we defined as k2 minus k1. So from x1 to x2, from x1 to x2. So this notation is an area under a function, which is the work done by the varying force. So the work energy theorem for a variable force states that the integral of that varying force dx is an infinitesimal area, or infinitesimal work done. We can call it the w. So f of x times dx is dw, where w stands for work done. Dw stands for a minute work done. From point 1 to point 2 is equal to delta k, that is k2 minus k1. So our only problem now is to find how we can calculate this area with ease. We can graph it, of course, and then on the graph sheet we use those boxes, calculate the areas one by one, and add everything up. But what if we don't graph it and we want kind of a mathematic way, a shortcut to do it? Now, let me tell you the answer to this. A very quick way to calculate the area, then I will prove it. So now, the integral of the varying force dx from point 1 to point 2 is equal to, there is another function we are going to create. Let's just call it g of x, and it is an area function. So it is equal to g of x2 minus g of x1. So we are saying that the total area under this curve is a function at x2 minus a function at x1. So if we know that function, we just put in x2, then we subtract that function at x1, and that will be the total area under this curve. So what is this magic function, g of x? Now, it is a function whose derivative is the force itself. In other words, f of x is equal to the derivative of that function with respect to x. That's how the force and that area function are related. And how did we know they are related? Let's prove that. Now, so we know this area function, g of x, is connected to the force function this way. Now, still on the graph, so we have the displacement axis, then we have the varying force axis. Now the force is not a constant, but it varies in dimples, ups and downs. So we are just saying that, let's pick an interval, say from this x to x plus delta x. That is, this interval is delta x. And if we do that, we can approximate that force to be a constant. Now, this has been exaggerated, okay? But the approximation is such that if the interval is so minute, then the force will hit the curve at one point. Okay? The force will be a constant, and the area of this small rectangle will be a minute work done, dW. You see. So we are saying that F at that point x, we call it at that point x because these two are very close. This is not drawn to scale. So times delta x is equal to now let's look at something here. Now the area of this small rectangle is the area from the origin. Let's call this our origin. So if we're able to calculate the whole of this area up to x plus delta x, from 0 to x plus delta x, okay, that area is dependent on the position x plus delta x. So is g of x plus delta x, where g is invented. We just call it the area function, g. And then the area from the origin to x is also a function of x. As x increases, that area increases. As it decreases, the area decreases. Same way as when x plus delta x increased, the area increased, and vice versa. So what I'm saying is that the total area under this curve is always dependent on the position. The area from the origin to x plus delta x is dependent on x plus delta x. As x plus delta x goes forward, that area increases. The area from the origin to x is also dependent on x. As x varies, that area varies. You see. So the area from 0 to x plus delta x is a function dependent on x plus delta x, which is this. And the area from 0 to x is a function dependent on x, which is g of x. So that is telling us that the area between x and x plus delta x will be that area function g of x plus delta x minus g of x. This is so important. Okay. But the bottom line is, if you know the force function, you know the displacement function, okay, then you want to find, so this is a force function, you want to find a tiny area between this point 1 and then 2. Let's call point 1 x and call this x plus delta x. See? Now, let's clean the x first. And you see the area from the origin to x plus delta x is a function which depends on x plus delta x. Because as it increases, the area would widen. And as it decreases, it will decrease. Okay. Then you want to also calculate the area from the origin to point x, very close to x plus delta x. That area will be this area, which will also be dependent on x, g of x. So the total area of this minute rectangle will be the area from 0 to x plus delta x, which is a function of this, and then minus the area from 0 to x, which is this one. And that's what we have here. So the force itself, f of x, is equal to g of x plus delta x minus g of x, where g is an area function. divided by delta x. And if we take a limit as delta x goes to 0, of g of x plus delta x minus g of x divided by delta x, then we call that the g dx in the language of calculus. So we are so lucky to discover that the mathematics is telling us that the variable force is connected to an area function of that same curve in such a way that that area function, if you take the derivative of it, you are getting the variable force. And if you know the varying force also, you can integrate it and then get the area function. So this is our work energy theorem for a varying force. So in summary, for a variable force, the total work done by such a force, of course, is equal to the delta K, the change in kinetic energy. But that is equal to an area under a curve, and that curve happens to be that variable force. If you know an area function at x2 and you subtract the area function at x1, that will be the integral of that variable force dx, the total work done under that curve. So this quantity is telling us the total area under the curve. So this function is an area function connected to position. So this is an area up to x2, this is an area up to x1, and the difference will give you the total area from x1 to x2, since we are calculating the work done from x1 to x2. Now, that is also good. So it means K2 minus K1 is equal to G, let me simply call it G2. Instead of G of x2, let me call it G2 minus G1. Let's group like terms. 2's to one side, 1's to the other side. We have K2 minus G2 is equal to K1 minus G1, or K1 minus G1 is equal to K2 minus G2. This is telling us that for a variable force system or field, okay, when that variable force does work in the system, there is a certain combination of speed and position which never changes. So if you move from point 1 to point 2, and the force does work from point 1 to point 2, that work done is a change in kinetic energy. But the sum of that kinetic energy and an area function, the difference between that, the kinetic energy minus the area function, is a constant throughout. So if you know that quantity now, you can predict it later on. So you trade speed for position and vice versa. Okay. But then physicists don't like the way this has been put because of the negative sign. So we define another function, u of x. Let's define another function, u of x, which is equal to negative g of x. So wherever we see negative g, let's put the u. So g of x is an area function, but then u of x is a negative area function. And we call u of x potential energy. So instead of k1 minus g1, in place of minus g1, we put the u1. So we have k1 plus u1. Let's note, this was just fabricated by physicists, since they don't like the idea of the negative, is equal to K2 plus U2. So this is kinetic energy. We call this potential energy. How did we know that this negative area function is a potential energy, or is an energy? It is because if this is energy, then the whole equation would relate energies. So then it tells us that in every force system, if the force is varying without friction, the sum of the kinetic energy and the potential energy, where the potential energy is a position function, the sum of those two quantities would never change from start to finish. If you know the total value for now, the total value later would never change. You trade speed for position. Now, let's recall that f of x is the g of x dx. But then if u of x is equal to negative g of x, then f of x would be equal to negative du dx. So g and u are negative of each other. Okay, so we would end the episode with the mass and spring system, and let's see how the law of conservation of energy works for that system. Yes, so for the spring and mass system, as usual, if you pull the spring, the mass from the equilibrium position to the displacement x, there's a force which is at the counter direction, F is equal to negative kx. And we are told that the work energy theorem for this varying force is that the kinetic energy plus the potential energy is a constant throughout, given that friction is absent. So if you pull the spring to this point, at this point it is resting, so kinetic energy at that point is 0. But then there is a potential energy, called, it has a position x. That potential energy, u of x, is a negative area function. That area function is g of x. G of x is a function whose derivative is the force. So the negative derivative of u, which is a potential energy function with respect to x, will be the force. So if you need the potential energy function, then it will be the negative integral of f of x dx. That is simple to do. Just multiply through by dx. Dx will cancel at this side of the equation, but it will multiply here. Then you have negative du of x is equal to f of x dx. And take the integral of both sides. And if you do that, and sending a negative sign to the other side, you have u of x to be that. So what is our potential energy function here? U of x. So u at x is equal to negative integral of f of x dx from at that point. You see. And that is equal to negative the integral of what is f of x. We know that to be negative kx, and then times dx. You see. So we have negative here, negative there. That will be a plus. So we have the integral of, let's bring k out, x dx from see 0.1 to 0.2. That will be equal to k. The integral of s ds is s squared over 2 plus a constant, say c. That will be u of x. Now, it doesn't mean we have to know the constant before we apply this equation. But it turns out that to balance the two sides of the equation, the potential energy at this point, u1, will have the same constant as the potential energy at u2. Those constants will cancel out. So eventually, this will be a definite integral because of the difference in the potential energy functions. See? Or in other words, the potential energy appears here and appears there. So those c's will cancel. So we simply clean that C. We don't need it. So for the spring and mass system, the potential energy function is K squared over 2. So it turns out that for the spring and mass system, half the mass of the the object v1 squared, pick any point, half mv1 squared plus half k x1 squared will be equal to half m v2 squared plus half k x2 squared. And this will never change. So half mv1 squared, or simply half mv squared plus half kx squared, is equal to a constant in the mass and spring system. It doesn't matter how you measure or where you measure it, you still get the same quantity. So if we measure the total energy at this point, when the kinetic energy is 0, the total energy will be purely potential, and that will be half ks squared over half ks squared. So that half ks squared will be constant throughout. It can be used to predict the velocity as, say, s equal to 0, etc. See. If we meet in the next episode, we are discussing more on the law of conservation of energy. Kindly subscribe, click on the notification bell, comment, share, and like my videos. Stay tuned.